Hello, in this video we'll explain multiplexers. We'll first define multiplexers and then we'll move on to explaining the multiplexer truth table, and from the truth table we'll obtain a Boolean expression to describe a 2-to-1 mux, and finally we'll move on to how to implement the multiplexer using VHDL code. A multiplexer is a data selector. That means if we have a 2-to-1 mux, for example, that means we have two inputs to choose from. In this case, it's I0 and I1. And at the output, we have one output. Hence, the name is 2-to-1 mux, two inputs and one output. For a multiplexer to work, we'll need an additional bit or an additional input called the select bit or the S value. Based on the value of S, or the control bit or the select bit, we'll choose whether to output the first input or the second input. This is the case for a 2-to-1 mux. If S is 0, we'll output the input that is connected to the label 0. So in this case, it's I0. If S is 1, the output will be equal to I1, which is the input connected to input number 1. We can have a 4-to-1 mux, meaning we have 4 inputs to choose from and one output, which is going to be one of the 4 inputs. For a 4-to-1 mux, we'll need 2 select bits, because if we have 4 inputs, we have to label them as 0, 1, 2, 3, so you can call them by their number. But for the purpose of this example, we'll deal with a 2-to-1 mux, where only one select bit is needed. And here we see the truth table of a 2-to-1 mux. We have S, which is our select bit, as the first column. The second column is I0, which is the first option we can choose from, and I1, which is the second option we can choose from. So Y is our output. When S is 0, when the select bit is 0, we're going to output I0. So that is going to be how we can fill the truth table. When S is 0, select input 0, and input 0 is I0 in this case. So here, Y will be equal to 0, 0, 1, 1. Again, S is 0. As long as S is 0, Y will be equal to I0. Depending on the value of I0, we'll just output it at the output. In the second half of the truth table, we'll consider the case where S is 1. When S is 1, that means we want to select the input connected to 1, which is in this case I1. So when S is 1, select input number 1, which is I1. So Y will be equal to I1. We'll look at the table. We'll observe that Y is equal to the values of I1 as long as S is equal to 1. Here we have the same example. This is the symbol for a 2-to-1 mux, except for input 0, we have A connected, or a signal named A. For input 1 option, our second option, we have a variable named B connected there. That means when S is 0, Y will be equal to A, and when S is 1, Y will be equal to B. So if we highlight that in the truth table, we'll notice that half of the table has S is equal to 0. Observe the values of A in this table, 0, 0, 1, 1. Y will be equal to the values of A, as long as S is equal to 0. When S is equal to 1, we'll select input number 1. In this case, it's B. So the values of Y will be equal to the values of B. Given the truth table of a 2-to-1 mux, we can create or construct a K-map or a count-off map, and from the K-map we can obtain the expression. So here we have 0, 0, 1, 1, and then 0, 1, 0, 1. We can group the ones together, and that gives us the expression Y is equal to not S and A, or S and B. That means the expression here is implementable using one NOT gate, two AND gates, and one OR gate. So this is the expression that we have. We can sketch the logic diagram for the expression, and from there we can implement it either using structural modeling in VHDL, behavioral modeling in VHDL, or even simulate it in Logisim, which is what we're going to do in a separate video. Now, to implement the 2-to-1 mux using one else statement in VHDL, we'll first start by declaring the library files that we need, which is going to be the first section of our code. The second part of the code will be the entity declaration. We can name the file or the entity mux_21, for example, because remember, the entity name and the file name must start with a letter. That means we cannot call it 2-to-1 mux. Instead, I'm going to call it mux_21 or mux_21. So here we'll say entity mux_21 is and mux_21. And inside the entity part, we have to declare the ports. We're going to start with the input ports. We have A, B, and S as inputs. Remember, our options to choose from are A and B. S is the select bit. So based on the value of S, we'll choose to output A or B at the output Y. So we're going to say port A, B, S. These are all inputs. They're of type standard logic, meaning 1 bit. And we have one output named Y. Y is an output of type standard logic. Now, the last part, which is the architecture part, is going to describe the relationship between the output and the inputs. And the way it works is, as we've been previously doing in other videos, we're going to say architecture behave of mux_1, which is the name of the entity, is begin and behave. So far there's nothing different or new. The only new part is the when else statement, and the when else statement is very useful for the 2-to-1 mux because it describes how the circuit works. And we mentioned earlier that the 2-to-1 mux, the one we see on the right here, can be described, or the output of it can be described as Y is equal to A when S is equal to 0, else it's equal to B when S is equal to 1. So this is what we're going to write, and that is going to be the when else statement, which is a behavioral expression. So we'll say Y is assigned a value equals to A when S is equal to 0. So remember the quotes 0, else B when S quote 1, when S is equal to quote 1. If S is a single bit, we'll use single quotation marks, as we see here. However, if S requires the use of more than 1 bit, for example, if S is a vector, or it's an input of type standard logic vector 2 until 0, then we have to use double quote for that. But as long as S is a single bit, we'll use a single quote here. Now this is the complete code for a 2-to-1 mux using behavioral modeling, or in particular using the when else statement. Thank you for watching and good luck.